Hello. Okay, let's get started. Okay, let's get started. Okay, perfect. So we'll start with machine learning today. Okay. Okay. So I am sure everybody knows where the code and the relevant stuffs are. Okay. Let me just show it a bit. So it is at this place. Right, this is the location of the code, and from machine learning topics, this is the guy 20, right? This is the phase that gets started. Okay, so second, yeah. Machine learning. So let's just start with the introduction of it, what it is exactly. Okay, so what it is, we're trying to, in a layman language, what we're trying to do, we're trying to create a software. Okay, we're trying to create an application which is not using if and else for logic, which is generating logic by itself, the way humans do, basically. Okay, when we learned identifying cat versus a dog, okay, our parents didn't tell us this is how a cat looks like, this is how a dog looks like, basically. Okay, what they told us typically was this is cat, that is dog. Based on the observation, our mind created the logic, isn't it? Okay, our mind created the logic. Using that logic, we were able to identify future cats and dogs. Sometimes we were incorrect. That is when they corrected us. Okay, and that is how it proceeds. So the logic, I mean, in regular software engineering, what has to happen? You write the logic. You write the complex logic, which should handle all the cases. A lot of if and else, a lot of switch cases. All of you have dealt it, seen it, right? So that is the way it was before. Now this part is all generated by the system. The logic is coming. You're writing a software which is generating a logic. It is equivalent to writing a brain code. Okay, so the entire machine learning has a lot of definitely history, and it weighs back 35-40 years back. It has undergone a lot of evolution. Till last decade, the notion was that it really needs a lot of computation power. I mean, the neural network part of it needs a lot of computation power. Even that is solved now, and the reason why machine learning is so much popular now is because accessibility of high computation. Right, that is the reason why machine learning is so popular now, because anybody, like even if you don't have a big company, you can make use of the high computation to solve your problems. Okay, now let's deep dive into it, what it is basically. Okay, so basically the entire machine learning, that means the mechanism by which software will be learning can be divided broadly into two categories. Okay, one is supervised machine learning, another is unsupervised machine learning. Okay, what is supervised machine learning? Supervised machine learning is that like if somebody tells you, if this is there, this is the result. If this is the parameters, this is the result. Like, let's take a case of predicting house price. Okay, if somebody tells you square footage of house is this, number of bedrooms is this, number of bathrooms is this, and the price of the house is this, right? So this sort of thing is supervised machine learning. Okay, where basically you are given the target information as well. Okay, the other side of it is unsupervised machine learning. Okay, what is unsupervised machine learning? Where you're not given this target information, you're given the data, only the data. Like for example, you're given customer information. Okay, only customer information, no target, nothing is given, and you have to find what are the groups of the customers. Right? What are the possible groups of the customers you can divide it? Like suppose you have 1 million customers, you want to do marketing for that. For that, you need to understand how to divide your customers best into, right? For that, what will you do? You'll try to find clusters in the customer. This is what is called unsupervised machine learning. Okay, understood at a high level what is supervised, unsupervised. Okay, the important difference between supervised and unsupervised is something known as target or label. Okay, a lot of jargons will be there. I'll be a little slow with jargon initially, then I'll try to add more. Okay, so there are a few things. One is let's take a small data set, huh? To see how the data looks like basically. For that matter, you have it here itself. Okay, so this is iris data set, one of the very popular data set. Every machine learning scientist should know this. Okay, iris data set. What is iris? You know, anybody knows what is iris?
I detect something.
I. Iris is a flower. Okay. Iris is a hotel also, but we're talking more about flower. Okay, see this. This is your iris. Okay, iris is a flower, and this is sepal. The smaller is petal. Okay, this bigger is sepal. The smaller is petal. Okay. Now, okay, so you can see here this is sepal length, sepal width, petal length, petal width, and the last is the level part. Okay, this is a 1980 botanical data. Okay, so what is the thing? This is some students were there. There is 150 samples. They calculated sepal length, sepal width, petal length, petal width. At the end, they also know what is the flower type. There are four types of flower, three types of flower: Sentosa, Virginica, and versicolor. Okay, three types of flower. Okay, so you have these four data sets and one this column. Okay, what is this? This is case of supervised machine learning, right? So if you give, after you have trained the software with, if this is the length of width, sepal, petal, and all that, and if this is the case, this is Sentosa, yeah, this is Virginica, or this is versicolor. There are three varieties of target. Okay, so it will learn, and later on when you just give the length, it will tell you this is Virginica or this is Sentosa. This is supervised machine learning.
So the target will be the level.
Exactly. Target in this column, you see species, right? Species is label, target. Okay, all these terms are interchangeably used, or dependent variable. There are three jargons that will be label. What is the label associated? Target or dependent variable. Okay. Yeah. Then, of course, supervised machine learning is broadly divided into two categories. Okay, one is your regression, one is classification. Okay.
Just one question. You gave this cat and dog example, cat and dogs. So that form, that is under unsupervised, right? Because you learn from observation.
No. So your parents told you, right? That is cat. If you are a kid, first time you're seeing a cat or a tiger, you don't know how to react, right? Because you don't know what is a cat, what is a tiger.
So it's a supervised?
Supervised. Because your parents will tell you that is a cat, that is a tiger. Okay. So supervised machine learning is broadly divided into two categories. One is regression, one is classification.
We need to go internals, like how we will generate the code now.
Yes, we need.
How machine learning will.
How it works. So the thing is, I take a blended approach. Okay. I first go little top down. Okay, little lessons. Then I go bottoms up. Then I try to connect them. Okay, this is what I felt. The learning is better. Okay, and you are more confident about it. Okay. So supervised machine learning is regression and classification. Okay, what is regression? Regression are super category of supervised machine learning where the output column that you're seeing here, right? You're seeing here the only three varieties: Sentosa, Virginica, versicolor. Three varieties. Okay. So regression, there can be n number of information. That means this is here in classification. This is a case of classification actually. Okay, classification means your output is discrete in nature. Output is fixed. Like for example, you will be given a tumor size and you have to identify this is cancerous or not. So what is the two classes? Cancerous or non-cancerous. Right? In this case, what are the possible three classes? Sentosa, Virginica, versicolor. Right? And the other option that we have, okay, is regression. In regression, what is the output? Output is continuous number from 1 to, like house price. Let's take a case. Okay, I'll show some house price data also. Yeah. You see this? Okay, if you want, I can load it so that you can have a better look. You can see this is price of the house. I think the last line or something. This is the price. Okay. If you want, I can load the data and you can see it. Okay. So this is, let me load the data. Yes.
Yeah.
Okay, read CSV. Yeah, you can see here. This is of course. Let's do. You see, you're generating index column. Index column. I think it is unnamed 0 is a column name. You can see here, this price is continuous in nature, isn't it? So this is the case of regression. Understood what is a classification, what is a regression? Can you give me some more examples of classification regression?
Male, female, classification. Male, female.
What are the data?
For example,
Gender, yes.
Students in the class, classified to male or female.
Based on their marks, based on their give a good problem.
Email is a spam mail.
Email, right. Email is there. You will identify with the spam or not. I'm asking the problems actually, which can be classified into classification. Okay, then anything that you can see across, come across. Huh? Mail is correct. More.
No, many are there.
Few more.
Trains. Transportation.
Transportation, predicting what time they will reach.
Like Indian Railways.
What time they predicting the time exactly. That's a case of regression. Actually, time series actually. Okay. Similarly, Uber.
Yeah, one thing is Somdev. In fact, you can use the same data set that you're using for prediction, and instead of using the price as Y, you can take the whole data set to segment the houses, and let the classification algorithm do the segmentation or the classification.
What is the end classes?
End classes would be so the point is for the problem statement could be to segment the houses, to do a house segmentation.
Oh, that would become you're not mentioning any class there. In classification you are mentioning class. That means, okay, breast cancer, yes or no. Okay, or say you are doing this email spam or not, news.
Oh, okay.
Politics or not. So when you say segmentation of it, it becomes actually
no, I thought in okay, yeah.
You're talking in sense of unsupervised.
Yeah, I was completely talking in terms of unsupervised. So yeah, I'm sorry. Yeah. Okay. We are talking about classification. Yeah, I'm so sorry. Yeah.
This famous is predicting wine quality without tasting.
Yes, exactly. That is actually a data set that will use wine quality. Okay.
Stock prices.
Stock prices again. It's a kind of little time series problem actually. Okay, you can say it as a regression case of regression. Okay. So and more so is like predicting given a news item is there, if it is fake or not, classification, right? Transaction is fraudulent. Although in finite applications you'll see around you, right? When okay, so let's proceed further. So we will so now what will we do is we'll learn it little differently. Okay, we'll not go we'll take an algorithm, will not go deep. Okay, first thing that we learn is how to use it, how to create a pipeline, how to solve problems. Remember, the foremost objective out of this course is you should be able to solve problems. Okay, so my focus will be creating a pipeline, solving the problem. Then we will go, gradually we'll go, layer wise. We'll finish this top level first. Okay, that is where you will be able to confidently use algorithm. It might sound little unorthodox, but this is what gives good results. I mean, by the end of this course, you should be able to solve Kaggle problem. You should be able to pick up independently Kaggle problem, then you should be able to solve it. That is the objective here. Okay, let's see. So there's a process. It's a process oriented. So let's run the process. So what will you do is, I'll just with this example, I'll just give a glimpse of what is simple linear regression. We'll try to understand what it is actually. We'll see mathematically and non-mathematically both the ways. Okay. So now let's take a case. Okay, so we all understood what is linear regression. Okay, so regression. Let's now just see what is linear regression in a superficial level. I'll go deeper into it. Okay, so that we can understand the first problem. Suppose you have a lot of this is your size of house. This is price of house. Okay, so you have a lot of this is this data here, right? Okay, understood, right? This is size of house, this is price of house. Then what you have to do, your software should give you a logic. Whatever we are writing machine learning code, right? It should give you a logic. Okay, using that, okay, first this is a regression case. That means we will teach it. We're just using one. This is known as independent variable or one parameter. Okay, one feature. The size of house is one feature. Okay, you can imagine if the data set is okay. If this is the data set. Okay, this is a data set, but we are not using all the columns here. These columns are known as features. If I use the term features, understand I'm talking about columns. Okay, but features has much more meaning, which we'll learn later on. Feature can be derived also. That means you can have floor into total floor plus total floor as a new derived feature. That also can play a very important role in generating algorithms. But as of now, for simplicity, I'll be talking features as each column. So you have this square footage here, you have price here. Got it, right? You have this square footage, you have this price. So what you have to do is you have to you have to write a software that creates a logic. If you give square footage, it will give you the price. Okay, we have to write a software that creates a logic. That is what machine learning you do. You write a software that creates a logic. You don't tell the logic. It will create a logic for you. And we will, using the first example, we'll validate that whatever logic we are giving, whatever logic it is generating, it's not that wrong, rather it's right. Okay, that is what we'll try to understand in the first one. Okay, now
Input the square footage.
price. Okay, so this is your square footage is the input, output is the price. Okay, so now if this is the data that I have plotted here, right? Square footage price data you're seeing. Okay, so what we want to predict, just a simple straight line. Okay, we want to predict a straight line like this, which becomes the best predictor, isn't it? We want to predict a straight line which becomes the best predictor. Okay, how many possibilities of straight lines are there? You have infinite possibilities of straight line. Okay, so there are few things here. You have to choose the best straight line. Frankly, you don't have to choose it. The algorithm will give you the best straight line. So we'll learn how does that, among all the possibilities of all straight line, how does the algorithm chooses the best straight line for, so that you get the best prediction. Okay, so what you will do is, for simplicity, okay, what we have here is this is your random number generator, nothing much, random number generator, right? And you are generating two data. One is you are generating 50 random numbers x. Okay, let's execute it. And you are generating y. You can see this. What is y? y is 2x plus 1.5. So what will this generate? It will generate this value, whatever you are seeing here, right? 2x plus y. So what this is, so for in our example, this guy became x, this guy became y, isn't it? Right? So and the point will be distributed for x and y, whatever points are there, it gets distributed over here. Understood? Okay, and there is a relation between this point, between x and y, which we have created. I didn't tell my machine learning algorithm that this is the relation, and what we want is we want it to find the best line. So what is the equation of a line? Mx plus c. Y is equal to mx plus c, where m is the slope of the line, c is the intercept of the line. Intercept where it is cutting this, that is the intercept. M is the slope of the line, right? Slope of a parallel, the slope of this line is 0. Fine. Okay.
What is y is intersection of the line? Y is equal to mx plus c.
This is the equation of the line. For if you know m and c, okay, you can say you know uniquely what line is this. For a different value of a different pair of m and c, you will get different line altogether. Okay, so this is the equation of a line. So what do we want to do? We want to predict a straight line. We're not with the simplest case actually. We want to predict a straight line, okay, which could do our prediction. Right? What we're trying to do, we are predicting a straight line which will be predicting a y for an x. Understood, right? So you have this y and you have this x. So for a x is, you can imagine in this case square footage, and you can imagine the price of the house is 2.5, 2 times of square foot, 2 plus 2 and 2 times plus 1.5 of the square footage. That is a relationship here. Okay, so if you have predicted a straight line, if you find the best straight line in future, if you have to predict the price of the house given the square footage 100, okay, what will be in this case? Exactly. Right. So if you find the best straight line, you will find the best prediction. So now let's see.
Why we have to find the straight line first?
Because it is simple. Actually, the reason why I'm emphasizing straight line is the equation becomes very simple here, so that we can easily understand and cross-validate. But essentially, we will do curvy line also. Okay. After this, we'll see curvy line. We'll see polynomial degree line. Then you will say why the hell?
So it's all the equations about that.
Exactly. You remember straight line equation, polynomial degree equation? Okay.
So it's mx plus c in the sense m is like something mean or kind of.
No, m is slope, some value. Slope.
It's just slope.
Slope of the line. Okay. So if this line is parallel like this, so the x-axis slope is 0, and if it is this is the slope of the line. Okay, it will be 1, 2, 3. Okay, depending on slope of the line. In this case, it is 2.
Okay.
C is 1.5.
C is 1.5. Okay, for this simple equation. Let's see now. Okay, so now we have x and y. We want to predict a straight line for simplicity. We'll later on see this part is very most important part of which if you understood this, other thing is just extrapolation from here. Okay, and let's see now. Okay, so what is the first thing that we are doing? We want to use scikit-learn for machine learning. Okay, so what for machine learning, and in this case we want to use linear regression of sklearn library. Okay, linear regression inside linear model. Okay, linear regression is a linear model. Okay, let's see now. So this is how you are importing the package here. Okay, then linear regression fit intercept will enable the intercept part of it, just a parameter. I'll come to that. So what you're doing here, you're creating a model here. What is this line? This line is creating an empty brain. Okay, empty, this I'm just mention this line, creating an empty brain, that means empty logic. This is not yet trained. Okay, you can imagine this as a brain when when a kid is born. Okay, no logic, no data it has seen before. Create empty logic object. Right, this is the thing, this is the model, empty brain creation. Then throughout scikit-learn you will find one function, fit function. Fit function is for training the model. Okay, what all do you need in this case to train the model? X and Y, right? Okay, but remember few things here. Okay, X and Y. X you are reshaping it to what is the total number of data? 50. And so we need to remember this. Whenever you are training a model, you need to pass each data in this format, rows or columns, like this. Each data should be like this. Right, you have this data, you have this data, you have this data. Each data is like this.
So it's always like 1 into 1. Like x-axis and y-axis. So it's 1 into 1 only, right?
In this case it is 1 into 1, but of course, as you saw the diagram, you can have number of bedrooms, number of bathrooms and all that. In that case you'll have 2 or 3 columns. Here will be square footage, right? Here will be bedroom, here will be kitchen, right? You have 1 column, so each data will be in form of a row here, right? Understood, right? That is why we need to reshape it. What is reshape 50,1 do? Reshape 50,1 will, so it is total, earlier it was 50 data, right? It will convert that into 50 rows of 1 column, because that is what machine learning algorithm understand. That is why you need to convert it into this shape, right? So if you do so, if you're doing so, you're training the model. First you have to create the logic, then you have to train the model. So now the model is trained, right? You can, of course, if you are doing a reshape, this is another way to do so, adding 1 more dimension. The data becomes like this. This is your X data. It becomes like this, rows of columns. This is optional to this. Understood, right? These both are same. You'll see one of these process everywhere, right? Then what you want to do, now that your model is created, okay, we want to really check whether is it we gave it X and Y. We didn't tell the relationship between them, isn't it? We want to really validate if the model found out the relationship or not. Okay, is it capable of finding the price of the house given a square foot, given a square footage or not? How will you do that? Model.coefficients. It will give you the slope of it. Wasn't this the slope that we passed it to? Right? This is the slope that we have passed it, right? This is the slope. Okay. Yeah. So from the data, it found out, the very important point here to understand here is, from the data, it found out the relationship between data. We have to tell it that, boss, you have to find a straight line. And if you tell it, it is able to find that straight line relationship between the data. If you tell it curvy, then it will find the curvy, polynomial degree relationship between the data. Understood what is happening here? Between it, what is mathematically, if you see what is machine learning, it is typically finding the relation, right? And what is this? What is the logic? The logic is a formula, right? It is a simple formula, mx plus c. You can have a complex one, ax square plus b plus c z square plus. You can have a complex formula which can represent your almost same thing, right? So what a machine learning thing is doing, it is essentially generating a formula for you. Using, if you fit all the inputs, you will get some output. That is what is. There is no magic that is happening. It is basically generating a formula which, for a given x, it can generate a y. Okay. Fine, right?
No, in general cases also.
Huh?
General cases also, like you're programming it like in C or something, like X is 2 and Y is the output. I need like 2 into X plus Y or something. So you are inputting into 2, it gives the calculation and given back to that result, right? So what's more difference between that and this?
I'm not giving it 2 or 1.5. I'm just generating the data. This is like this process is like that we are validating that if machine learning works or not. Okay. In this case, we are anyway passing the relation. We know the relation. It's like if you want to validate some product, you know what is the input and what is the output, isn't it? And what is the relation, right? That is what we are doing it here.
Some input we have to give.
Huh.
Little.
Right.
Yes, we are writing the logic. In this case, it is writing the logic.
Exactly. So here we are giving the relationship because we want machine learning software application to tell us the relationship and we can cross validate if it is really doing it right or wrong. Okay, so just take a step back and think what just happened here. You have X and Y, only you know the relationship. Actually, what you can do is, I can change it. Right? I am not seeing it. What is the key I'm pressing? Okay, I'm not seeing it. I don't know what key. Make sure I'm pressing a number here. Am I? Yes. Okay, I don't know. Okay, then I'm trying to go little. Then I'm changing it to some. Is it perfect? Yeah. I'm executing it and go down. Okay, I'll be again training the model, right? I haven't seen it actually, only you guys know it. Okay, is anyway the part of the data. If I do this, is it right? Is this the word that I pressed? Right. So that's what. So for me, I don't know.
So that's correct. I think what you were asking is here we give you like y equals some formula. You change the number to b. So regularly also we do this.
No, absolutely not. This is
logic can be some formula.
No. This formula we use that formula to generate the data. Okay.
What we give.
So just see the data below. Suppose you see this data. Here there is no such logic. If you see the data here, there is no such logic. Right? This is your X, this is your Y. Right? In this case, I'm not showing a relation. But how do you validate whatever the algorithm is generating that is right or wrong? So we created a data so that we know the relationship. How will you?
It's just for testing you are telling. That's all. It's not like how we pass it.
Right. That's not how. This is just to test whether the linear regression function works right or not. Given the data, is it able to find a relationship between that or not?
So all the supervised, unsupervised, all these algorithms are used for model training.
Yes.
So when I get an input like image or text, some processing I have to do so that I can get this in an array form, and then feed it to supervised and unsupervised.
Right.
So first we have to.
Some processing should happen before it reaches this stage. On text as well as in image.
Right.
So what are those algorithms which process the data?
We'll
bring it to the array.
Welcome to that. This is the first class.
So that is also part of machine learning.
Okay. So if you do coefficient, it is giving coefficient. If you do intercept, it will do, I made it 145. Right. So it is exactly doing it. Okay. So now you give a data for which you don't know the relationship. It will do. You trust it now, right?
Yes.
How to build a trust? You first need to test it. Then you can trust it.
So this is kind of a validation we're doing at this stage.
Right. So you're seeing it first time. So how do you trust really? Will it really do it if I give the data? Will it? I mean, don't you think that will it really? If you're trying to sell your car, second-hand car online, whatever price it predicts for you, do you think sometimes is it really showing me that this result? If for my car, if I try to sell it, it might show me less numbers, and I'll never, being the owner of the car, I'll never believe. No. I think it is more than that. Right. So you need to have trust before you can use the prediction logic there, right? So that is where first we are seeing if it is really working out for us. Okay. Then we will use it to solve it. Understood? What is simple linear regression? Okay. Now you can go a little deeper here. Okay. Now using this logic, if you want to predict Really? Okay, so you can do model.predict, pass the data here for which you want to predict. Okay, pass the data here. 7 it is 7.202, I think is the last number or something like that. Let's see. I don't know where is 7.2. Some number should be there. You can pass 12 point this and see if it is predicting right. Huh? Last number, right? So that we can anyway see the output. So it is 246. Huh? So let's see. Let's print y. Oh, 12 point. Achha, I think I'm printing the older value. Oh, 5.6 this one, no? But this one actual y is 12 point this one, right?
No, actually this
189 only.
is right.
189 only. See this, it's right. Right? 189, same, almost same. Okay, so this is a straight line. What we will see in near future is how to predict this polynomial degree. Straight line means the output will be this, isn't it? Polynomial degree means the output can be this, right? If you have a quick question for you guys. So if you have 3 points and if you have to find a line which touches all these 3 points, what is the polynomial degree that is required? You have 3 points. You have to find a curve which touches all these 3 points. What is the degree of polynomial? Second degree, third degree?
0 degree.
0 degree. 0 degree means? Yeah.
Yeah, second degree, I think should be fine, but it will go down further. Avantik, I think second degree will fit it, but then if you extend it further, it will further go down.
Achha, so if I give you 5 points like this, then?
Then I think third degree, the cube fits that.
So
the third degree will fit that. Yeah, third degree.
Yeah, maximum degree that you need is n-1 basically. If you have n points, with maximum of n-1 points, n degree, you will be able to fit it. That is the maths.
Okay.
Okay, maximum. I mean, it can be lesser than that. Okay, so remember this line. So if you have 1000 points and you have to make sure a curve is there which is touching all the 1000 points, you might have 9 degree polynomial. Might need, but that is of course not the best case. We'll learn these things. Just put for further. If you want, you can note it somewhere. Okay, just got a glimpse of this, right? Okay, now the question is, okay, which must be there in your mind now. How this guy, it actually predicted your slope and intercept, isn't it? What are the range of possible slope and intercept? Huh? No, for not particular straight line. What this line predicted you? This line predicted you theta's slope and intercept, isn't it? Each straight line can be uniquely identified by a pair of MNC, isn't it? Right. So it predicted this straight line for you. It predicted this MNC for you. Now the question is, what are the possibilities from which it is predicting you MNC? Infinite, right? So how does it find you the best combination of MNC is using something known as gradient descent. Okay, so we will see something mathematical now. Okay, little more mathematical, and using that we'll understand how is it finding for a particular line. We are talking only about straight line. Remember this. For all possible straight lines, how it is finding the best combination of MNC. Okay, so it will be little mathematical, but very easy to follow. This is the page from which I'll be showing some degree and all that.
So supervised, unsupervised, they don't find the best. They just get the data, and on top of that, we have to apply some more algorithms to get the best.
Do we have to apply linear regression to get the best?
Okay.
You have to apply linear regression or Okay.
No, my understanding is you get the raw data after you process image or text, and the raw data you represent in the form of an array matrix, and then you apply supervised or unsupervised algorithm. You get some possibility.
Some model, yeah.
Yeah. To pick the best model, you have to apply this.
No. You don't have to do that. Okay. So few things you are mentioning correct. Few things need some. We will understand. Just give me some time. Okay. I'll
So this new whatever you are.
gradient descent. I'll come.
So that is part of supervised.
That is part of supervised. Yeah. Part of finding the cost and all that.
So on
Few
top of
minutes.
linear regression.
Few minutes. Let me go there. I haven't yet spoken a single word about it. Okay. So this is according to this note. This is how they have represented this thing. Okay. H theta x is your y. Okay. Some notation. That's it. Okay. I'll mention it. This is your y. Theta 0 means your intercept. Right. Theta 1 is your slope. So this is the equation of the line that you have to predict. Similar thing, just the notation changes here, nothing much, and just for simplicity of explanation. Okay. Then the point here is we first have to understand what is cost function. Okay. So what is cost function? Let me first clean this. Okay. So what we are trying to understand now, what is cost function, and cost function is very important part of machine learning. Okay. So what will you do is, suppose we have this data here. This is the data. Okay. We have to predict a straight line, and let's assume this is a straight line. This is one of the straight line. One of the possible straight line. This is not the final one. This is one of the possible straight line. That is the question, right? If you have a lot of straight lines possible with different values of m and c, how do you find the best straight line? Okay. So among all those possibilities, I'm just explaining you what one straight line. Then we can extrapolate. Okay. So this is the prediction line for this particular data. This is the x, and this is x. And this is y, isn't it? This is y-axis. Sorry. Okay, this is x and this is y-axis. So this is the cost that it is predicted. This is the actual cost. For this line, this is the cost that is predicted, and this is the actual cost. This is the actual cost. So actual price. Right, this is again square footage, and this is price.
So just what is actual and what is predicted? What is actual and what is predicted?
Yeah, this is the actual data actually. So this is actual.
Actual price it is.
Yeah, actual price, and this is the point. If given this particular data, this line will predict this as the predicted data. So this is the prediction. Understood, right? What is actual and what is prediction? So what will you do now here is you will try to what is your cost function? Basically, cost function is difference between actual and prediction. That is the error, isn't it? Cost is nothing but error, right? So the actual price minus prediction price, or the reverse, doesn't matter, because you are doing a square of it. Okay, and the reason why we do a square of it, what happens if you square a very low number? Again smaller, right? That means insignificant things become more insignificant. Okay, if you square something a little significant number, it will become more significant, right? Okay, so that's the part of that is the reason why so what is the cost function here? The cost function is basically this. What is your h theta x? Is the h theta? See the notation. Xi means for ith house. H theta of xi means cost prediction of ith house. Okay, minus yi means actual price. You're doing a difference of them and squaring of it. Right, difference of it and squaring of it. Okay, and for all, what are the total number of houses in this case? Total number of houses is m.
Yes, yes.
M is total number. So what is sigma 1 to m means? You will sum them all. Fine, right? So there is cumulative error. Now what do you have to find? You have to find mean error. Mean error, that means you will divide after this mathematically you have to do square root. I mean you have to square root of this to normalize the square. Okay, and that is what is your thing, square root. But you know, mathematically it is equivalent to doing 1 by 2m. Okay, just see, there are a lot of things in such machine learning, or if you do a lot of mathematics studies, right, a lot of things where they will find do equivalence of it. The reason older days, if you reason out for the actual, one of the main reason is older days calculators, computers were not there when these things were proven. People have to do those maths by writing themselves. Understood, right? That time it was very difficult to find square root of all the data. It was easier to do 1 by 2m. Understood, right? Okay, so this is equivalence, because anyway we don't want actual cost, we want comparative costing, right? So in the software you will find 1 by 2m in code, right? So this is the cost of this straight line. Okay, so there how many possible there can be many such straight lines. There will be different cost for each line. And what is the line that you will choose? You will choose the line which has least cost. Right, and this process of choosing the line with least cost, I mean the mechanism with which you choose the line with least cost, is known as gradient descent. We'll learn what is gradient descent approach. But what is gradient descent? Gradient descent is used for choosing the line which has the least cost.
Why do we want a least cost line?
Because least cost line means less error, isn't it? Your prediction will have less error. Yeah.
Can you give me that sum again? It's not very
This is the prediction. This is the prediction here. This is the actual value. So you are doing prediction. It doesn't matter what is the order. Anyway, you are squaring it. Prediction minus actual value is your error. Right? You are finding error for all the points that you have. Total number of m points are there. That is why you're doing sigma of 1 to m. Then you are doing a square root. And doing a square root is equivalent to doing 1 by 2m mathematically. Okay, doing a square root is finding a square root of the result, right? Yeah. So doing a square root over, I mean, when this was designed and all that, okay, it was not an easy operation to do. Square root is never an easy operation to do. When it's designed in days where there was no calculator, no computer, right? So they found out it was equivalent to 1 by 2m, almost equivalence. Right, okay, so okay, you can see here almost equivalence, because there will be only minute differences, and this guy apparently became the cost function. Fine, right?
So this is the prediction cost of
this is the cost function of this line
of the
line. So different line will have different cost function. Okay, so what you have to choose, we have to choose the line which has the least cost function. So this is how you represent it. A j, you have to find the best value of theta 0 and theta 1. Okay, you have to find the best value of theta 0 and theta 1 for which the cost function is least. Right, so j, this is the notation here. You have to find best value of theta 0, theta 1. Okay, so what do you have to do? You have to minimize j theta 0, theta 1 by changing theta 0 and theta 1. Understood, right? You have to minimize j theta. This is the cost here. You have to minimize the cost by changing theta 0 and theta. This is the notation in what it means. Understood? Minimize theta 0 to minimize cost. How the cost is written as j theta 0 theta 1, and you have to minimize cost by changing theta 0 and theta 1. Huh?
Theta 0 and theta 1.
Hey, this slope and intercept. This line, this line, this line, this line, this one, theta 0, theta 1.
Okay.
Got it, right? Slope and intercept. Keep the notations in mind. It's very simple. Just the notation makes it very tricky. So that's why I keep repeating.
But that will be changed automatically by the algorithm, right? And give the best prediction.
Yeah. I mean, theta 0, theta 1.
Yeah.
Yeah. That is what gradient descent does basically. Okay. So let me explain. For simplicity, okay, you'll see this thing. You'll remember in school when you're doing all this stuff. You used to remove all this term for sim. You used to write this one equal to an tilde sign above it, right? That means equivalence, not equal to, right? So we'll do here. So for simplicity, what you are doing, you are making theta 0 as 0, the intercept as 0. So what is the line that eventually boils down to? Or you only have theta 1. So j theta 1, and you have this. So what you have to do, you have to minimize j theta 1 by changing only one variable, theta 1, right? So now you have only one variable, right? So you are plotting a graph here for cost. This theta 1 is your theta 1 is your x-axis. What is theta 1? The only variable that will change in slope of the line. The j theta 0 is the cost, right? J theta 1 is the cost. Okay, j theta 1 is the cost. And when you're plotting the curve here, right? When you're plotting the curve here, what does it mean? When theta 1 is 1, the cost is 0. When theta 1 is 1.5, cost is some 0.5, and so on. Right? Okay. So you can see what you are plotting here. I mean, for the simplest case, this is so simple that it won't happen in real life. Okay. So this is so okay. For the simplest case, you have a curve here. What do you have to find, and what is the best theta 1 for which you are getting the least cost? 0. This one, right?
Sorry,
1, right? Best theta 1. So what you have to do from a curve, basically, you have to find that point at which the slope is least. But what is slope? Slope is this line, isn't it? What is the slope at this point?
0.
At this point, slope is something like this, isn't it? Sorry. Slope is something like this, isn't it? At this point. If you have a curve, if you have to find slope at a particular point, what is it? It is d by dx of that curve, right? At that particular point. Okay. So what is d by dx? D by dx is change of
The particular value depending on how much data.
when you do d by dx of speed, what do you get? Change of speed. That is your acceleration. Speed is there. So what is acceleration? Change of speed is known as acceleration. Okay. Change of slope is known as change. If you want to find what is the slope at a particular point, that means what is the change of this degree, you do d by dx at that particular point. So if you do d by dx of this point, what will be the value? What will be the slope? 0.
It's
So you
acceleration or velocity?
velocity and speed are same. Just that velocity is vector where you have direction associated. Speed is a scalar. Right? So if you see here, you have to find that point in the curve at which d by dx is equal to 0. D by dx of a curve, okay, tells about slope of that point where you are applying d by dx. Okay. So in this curve, if you see here, d by dx of what is the slope of a straight line? 0. So d by dx of the curve at a point where it is equal to 0 is the point at which the cost is least. Agreed? Right? At which the cost is least. Okay. So who does this stuff? This stuff is done by your gradient descent. Okay.
But this algorithm can be used to find both scalar and vector data.
Sure.
To find minimum cost, we're saying it's an acceleration, right? So we can use this function for both scalar and vector data, or
doesn't matter, right? Doesn't matter. As long as you have cost information, the only information that you need is cost. Right. Now just imagine with NumPy. So this is just 1 theta. If you have a complex line, lot of curvy line, you'll have lot of, and you have this theta is your slope, right? Okay, so you have a lot of theta 1, theta 2, theta 3, right? So you can imagine that is where your n-dimensional space things are required. Right there, what will you be doing is you will be, like if you just increase theta 1 by 1 more theta, it becomes 3D curve like this. What you have to do, you have to find the point at which the cost. This is the cost. You have to find the point at which the cost is this, maybe this point.
almost is already at the bottom.
Yeah, it should be the lowest point of this is the cost, right? This is the cost.
So always lowest means when last is lowest. Cost means always it will be lowest point.
Yeah, because we want the cost to be least.
So always it will be 0.
No,
Not necessarily zero.
the maximum also some cases.
Right.
Another situation. Some
It can be non-zero. So like in this case, it is not zero. Right. Not necessary cost will always be zero, right? But you want the least cost among all the possibilities. You want to find the least cost
to buy a house for that particular.
No, this is not that cost of house.
Okay.
This is the cost of you. What we calculated that 1 by 2m sigma of 1 by m h theta xi minus yi. This is the cost. Cost means what is the actual value minus predicted value. Some cost of a line. I'm not talking about the cost of a house actually. I'm talking in general cost of a line which is predicted. Because that is the error, cost/error, whatever you say, right?
So in this scenario, how we can apply it?
It has already been applied. When we do this fit function there, right? When you call, and this is all internally happening. When you call the fit function internally, what it did is it generated all possibilities of theta 0, theta 1, found out which one has the least cost. So it realized a line with slope 2 and intercept 1.5 has the least cost and gave you that. So all these things we don't have to do. It is doing it for us. Understood, right? What is happening? So for you just have to call fit function. Okay. Using fit function, the model will find the best slope, best intercept.
So basically the fit function is a logic that we write in real life.
Right. Internally, all this gradient descent, everything is happening internally inside fit function. Fine, right?
And
Correct. Where we apply this actually?
You are not applying this.
No. I mean this
application.
In application, what solution we are getting it on top of this?
Best fit.
And get you.
See, these are the things that is happening internally.
Correct.
When you run a Java program, there is a JVM which is compiling the bytecode and all that, right? Okay, so you don't use it, but it is happening internally. You know it.
Yeah.
You know it so that you can understand it, because there are a lot of other things we'll learn. Okay, so you can understand, and later on, if you try to write your neural network code and all that, then your understanding of this gradient descent, all these things is important. Okay, don't worry. I mean, the thing
It
is
is internal to the model.
Yeah,
They
it's-
just
Not application as a real estate price.
Correct. See, in this case, like 1,000 square feet is like 2 lakhs or something like. So we have a bulk of data. We are pushing into it. We need a best square feet with a least cost.
Yeah.
In this situation only, we are applying this, right? For that requirement. You mean to say no?
No.
Or I'm wrong?
So when you see the cost, the cost were confused. Okay. So when I use the word cost, right, I am not talking about cost of house. Okay. Yeah, I'm just talking about this is mathematical part of cost. What it means, what is the actual value that is there, the price of the house. I'm not using in the entire thing. I'm not using cost as house price. For house, I'll use price only. Okay. So what you're doing here, you have actual house price versus predicted house price. The difference and whatever we discussed this, right? That is the cost of the model, the line.
So you mean to say now what's the least cost if we pick it? That cost
Becomes
where it equivalents to price. Does the price is the least? I mean the
least cost.
optimal price for that square feet.
Right.
That means to say.
Right. And that is, you don't have to do this. All these things, like fine. Like when I see the code. Okay. So when I see the code like this, okay. When I did a fit function here, right? You are putting that x and you are putting this y. Okay. And it is internally generating you coefficient and intercept, right? So that means it is internally applying gradient descent, finding the least cost line, and it is giving you slope and intercept of that line. That is all. Where is gradient descent being used? Gradient descent is being used when you call fit function. Clear, everybody?
in same prediction, just a high level, how does it work in R or Scala? The same thing.
Same thing. This is algorithm doesn't changes. The R, Scala, whatever you say, right? Okay, they are just implementation changes. Logic is
Do
same.
they use the same scikit?
No. They have their different level.
Different one, but same function.
Same function. Okay. Okay. So just to repeat, okay, in one line, okay, there are only two things that happens here. One is, when you call fit function, you just pass x and y. Your algorithm will generate you theta 0 and theta 1. Right? What is the output of fit function? In this case, theta 0 and theta 1. How is that generated? Internally, gradient descent is used. Gradient descent will find cost of each possible combination of theta 0, theta 1. Okay, and it will give you the best theta 0, theta 1 based on if the cost is least compared to others. Okay, after getting the coefficient and intercept theta 0, theta 1, you can use this guy to predict future house prices, given you have the square footage of house.
Future in the sense?
You can use this to find out, given a square footage, right? It will be able to predict the price of the house.
It may, I mean, the prices were increasing. So in future, if you want to use the same thing, so again you have to pass the real-time data, right, for that.
Yeah.
So that you will get the best results.
Absolutely. That means your data is very important part of machine learning steps, right?
So
you have to make sure that your model is updated.
Yes.
Right. Okay, so what you saw in this case is typically just one straight line of it, isn't it?
Fit equal to linear regression. Fit function is equal to linear regression.
No, fit function is universal training function. Okay, so with this you will be doing training and all that.
The same scikit, apart from fit, do we have any function?
Predict. Using that we predicted. Okay, so a lot of such functions are there. Okay, fit, predict probability. It will tell you its probability. So a lot of these APIs are there.
Is there any keyword, like where I can see all those things like?
Model name dot you give, right? Model name dot. Okay, now
Linear regression first and then fit.
First you have to create an empty model. Okay, so this is saying that you will write code throughout. Okay, like even if you don't know, like for that matter, I can give you that's what my next stuff is. I will take an example for that I haven't spoken about what it is. All I will tell you that is a classification algorithm. Okay, see this case. What I'm doing is sklearn neighbors. This is later on we'll study neighbor classification. So this is some algorithm that I haven't spoken to you. You don't know anything about it. All that you know is typically that it is a classification algorithm. Okay, so you can see and neighbors. You're giving someone you don't know. I don't want to talk about this algorithm also. Okay, for you it is a black box. Let's now see how to use it. Okay, this is the case of classification. That's all you know. Okay, so you have X and you have Y. You have to train the model. So let's see. So this is the again iris dataset I'm loading. Okay, load iris. The sklearn datasets has inbuilt lot of datasets available. One of them.
It's imported all everything.
Right. Now this is your Y data, which is the content. This is what is your y data? As we saw earlier, it has three possible varieties of it, right? Sentosa, Virginica, and versicolor. So that is why 0, 1, and 2. X data, if you print X, 4 columns. Understood, right? Yes. So we want to do a simple case of this is a classification algorithm. That's all you need to know now, nothing else. Okay, the classification algorithm. So you created an empty model here. Then what do you do? Same stuff, fit, and X data is already in rows format. You don't have to convert it, and Y is anyway in 1, 0, 1, 2, 3. Okay, model is trained, right? Then you want to do the prediction. Pass X to that Y model, it will be prediction, right? So if you want to really compare Y model, see this, it's very much similar to whatever we have actual data, right? Predict. Whenever you're predicting, you're passing the data and it is doing the prediction for you, right? So this is a simple case. Okay, but how do you find out? Now I'm focusing more on the process part. Till this point,
there is a coefficient that does not take care of them.
Here, no, here in this case, we are using some that is we are not using linear.
Cost function is not using.
Huh?
Cost function we are not using.
No, cost function we are not using anywhere actually. In earlier case, I just explained it internally. That is how linear regression works. Okay, so similarly, internally those things will work. Here, what we are doing it simply we are calling the fit function.
Just classifying.
Right. So, and what is output? See, that's what actually you need to accept here. Okay. Because this is what common question I get. You know, machine learning is. I mean, of course, mathematical parts are inevitable here. Few things you need to understand, but trust me, that doesn't block you anywhere. Practically, when you're using it, right, most likely what you'll be doing, you know, for solving a particular problem, you have 10 solutions. What will you do? You'll apply those 10 solutions. You write. You're engineers here. You'll be writing very flexible code. You'll write a code such that it will run 10 solutions overnight. Keep the results in a file, or it may mail you. Just run it. Go home. Sleep. Tomorrow morning when you come, you'll find this algorithm give you this much % result. This algorithm give you this much % result. You choose the best among them. So it's a process. It's a process. Okay, knowing the internal part is really interesting and good. Okay, but having said that, in the entire to solve problems, it will never block you. It might give you that extra edge. Okay, so focus on the process part in the beginning. So coming back to here, so when you are doing a fit X and Y, right? You're training the model, then you're doing a prediction here, right? Then of course, now a very important point here: how do you find accuracy of a model? This earlier we saw a regression, right? Now we are seeing a simple classification. Just a glimpse of. We'll go deeper into algorithms, but now a glimpse of it. So what you want to do? You have your sklearn matrices provided you accuracy score. Okay, this is the inbuilt function. What do you do? Accuracy score. You are passing actual target, comma predicted target. Right? In this case, it is giving you 100% accuracy. Why? Yeah, that is true. Zero error. But is it good?
No.
Huh? It might be fake. When something is so true, so correct to be true, you should first doubt if it is wrong or right. Right. So it is actually not same here. Why?
Actual and predict should be different.
Huh? Yeah, you see something interesting, huh? Tell me.
Actual and predicted should have some difference.
Some differences. Yeah, I mean, it's not God. It cannot predict everything correct. Right. It is just a maths. It should work. Sometimes fail. Right. And so what is wrong here? So what is wrong here is you trained, like it's very similar, like you went to exam, you got the book from which all questions will come. You read all that book, you went to the exam, gave all same questions came. This happened to me actually once. So say, but is it really test of your knowledge? Is it test of your intelligence? No. But you still get good marks. Right? So that is
That is important.
Marks. Okay.
So how to introduce error in this?
No, you don't have to introduce error. You have to predict it right.
It will
Okay.
separate test and
Absolutely, and that is what we are doing next. Okay.
What is acceptable variance? The accuracy percentage.
There is,
100 is fake.
you can say there is actually different phases of it. Okay, so if you are creating a software which is in an initial stage, it needs more learning. You would say 70% thing is fine actually. If you are doing a chatbot, right, and 70% time it is recommending you the right answer, you'll be fine with that, right? You don't need really 100. But if you are in a email spam, right, if you got a job offer of 200% hike and it goes to a spam folder, you'll kill Gmail, isn't it? So that's what actually. So it depends. The answer to that is it depends on the application. Depends. Right. It depends on many other factors. So there is not really a case. If you are predicting whether a news is spam or not, right? If you're predicting that with 70% accuracy, that is fine, right? That is a good alarm for the reader. That 70%, if Facebook comes with that news, that information, 70% chances that this information is fake. Okay, I'm sure they are working.
But anyways, we cannot increase the accuracy because we are anyways using the subject related.
No, we can.
But see,
There might be the point we start thinking that this is the best accuracy then or
because anyways we are using the best features we don't get able for that particular data set.
for that model. But what there are many other parameters. Okay, you have this is one particular stuff you're saying. But now you have your data, which are the fields that you're using in data to do this. That also matters.
Yes.
So number of parameters increases.
Number may not be. Okay, so everything depends. So that is where there are many variables here. Okay, as an engineer, you should be very conversant with the process of how to churn through all these parameters and still get a reasonable answer. I mean, it's an iterative process. You will turn with few parameters earlier, do some prediction, see, oh no, it's not doing good, let me change something here, again try it here, then you'll add some more algorithms, add some more hyperparameters, then you'll see what will happen, right? It's a continuously iterative process. Okay, it's not that you write a code, finish the code, it is done. It should continuously be iterated, see if you can improve it,
What is hyperparameter?
We'll come to that. Hyperparameter is just a glimpse of it. This is hyperparameter, you can say. Okay, the initializer of models. These are known as hyperparameter in machine learning systems. You have n neighbors is equal to 1. You can have 2, 3, 400. Right? When you initialize models, but the arguments of it are known as hyperparameters. These are training model initializers. Okay, so see, we'll come to the finding the best hyperparameter. That is known as hyperparameter tuning. Okay. So you found the accuracy here, right? Now what will you do to test the actual stuff? What will you do? You will actually divide the data into two parts. What is train test split inside model feature selection or?
So this was the connection. After we get 100% of it matches with the input, we have to change the input parameter. And there's an exact match between input and output. We have to change the input parameter.
No. It's not that what we wanted to discuss over there is if we want to have a good model, which is, I mean, we don't want only for this data, isn't it? We want a production ready model which should be working in all the cases. How do you validate it? Right? How do you validate that the model is good or not good? What is the variance? What is the the parameters? Right?
What should I change in that case?
So your question is a little wrong here. So what you should be asking is, how should we make a better model? Okay, because that was a fluke case. We trained the model with the same data. We tested the model with the same data. That is a fluke case. That is not what will happen in real world, right? In real world, you should be when you're preparing for the exam, you should be very well aware of the fundamental concept, so that whatever question comes, you should be responding from that. So you need a more generalized learning there.
So regarding the first part, can we predict like future CAT exam questions? Basically, those kind of things. It takes time for like providing the past cases.
But it is two things here actually. So
Again, the
No, I
input
don't
data
think
what you are providing depends on that it
Machine
predicts,
is
right?
not setting the questions, right?
Has anyone tried?
No, that he has to.
oh, you are getting wrong direction now. Okay, so if you're predicting questions, there are two things, right? One is
The input which we are giving depends on that it predicts something, right? So input data, if you know it,
Exam, the kind of those things that differs. What I'm asking is, in your classes, somebody would have tried to for the past
predicting
cases.
questions.
KBC questions.
You cannot predict because it is
So-
not sent by machine, right?
yes.
It is not sent by machine, right? The question
But
is not.
humans, everybody comes with their background. Because it happens in UPSC.
What if I change the examiner this time?
Yeah, let it finish. Yeah, carry on.
So that's what I was saying. Has anyone tried?
Nobody has
Any
tried.
project?
Generally, you try to predict answers. Okay. Definitely questions. It becomes very abstract because then I'll tell you there are the closest thing that I know to this is you can predict answers, text answers. Like if somebody asks you how are you, okay, there are a lot of things around, lot of application which finds the best answer for it, right? So then okay, then they can strike a conversation. Okay, then how do you validate if the other person is a human or a bot, right? They can strike a conversation. He will be asking some question, the bot will be asking some question. That sort of things to a certain extent.
Like capture nowadays, it comes with the pictures.
That is very basic stuff. Yeah, the bot is like when you chat to many backend thing, right?
That is what recently Facebook was faced and they closed down that robotic
It's on that scale.
Bots.
Bots, yeah.
bots.
So when we go to a website and try to interact with the chat window and all that, many times there are bots in that place who will be talking to you.
Yes.
Right. We can figure out at times, but if the bot is written too well, we may not be able to figure
So
out.
nowadays, we like 10 pictures. We say identify signs in this randomly because capture you can usually overcome it. Many bots can do.
Right.
So now they come with the image that is like bots can bypass that. Will come with something else.
Right. So the thing is, this is still like I used to show this thing, cat sitting on a dog image. This is still in the process, but I hope someday it doesn't come up with this predicting cat questions and all that. Okay.
It's accuracy. 50% accuracy.
Oh, predicting questions. Like how can you generate? As of now, I don't think.
Because the institutes, like any coaching centers, they do predict based on previous papers. 10%, 5% it comes. So that is their prediction. That is their accuracy. So we can do that.
Oh, you're saying that way. That means predicting from existing questions.
Existing. That's what they say. 20 years. Data
So that you can, but you cannot generate question. That is what I was more towards.
Yeah, that's what it is.
Predicting these questions possible in the next exam.
Hmm.
That you're predicting a question. Actually, may not be the same verbatim. May not be the same verbatim. But this topic.
To some extent, you can. Again, if you don't know still, will it be better than a random guess or not? Right. To some extent, you can. Based on the previous question pattern, you're saying. But okay. Okay. Let's get back. Okay. So I was talking more in terms of train and test bit. Okay. What will it do? It will try to divide your data into train data and test data, so that you train your model with one data, test your model with another data, so that you find a better model. That a lot of models are competing with each other, right? Okay, you're the one which is promising you better results. Come up, right? So you need to validate. So that's what we are doing here. So you have the data x and y. You are dividing it into two parts, 0.5, 2 parts. Okay, and it results x1, x2, y1, y2. Right, x1 and y1 you can see here x1 shape, x2 shape 50%. Okay, right, total 150 data, it has 70, 75. Okay, now you are training the model with the x1 half 50% of the data model, right? You are predicting with the next 50% of the model. You are finding accuracy. First is the actual value, next is the predicted value. You see, now it has come to 90%. Understood the second process?
Normally we always take 40% or like
No, 80-20, 75-25.
So depends on the type of data.
Mostly 75-25.
Is there any difference on the data type of data? Is
Huh?
there any difference in the type of data or type of problem that we solve?
No, it's most standardized 75-25. So you want to use 75 for training, 25 for validation. Okay. There is another approach. The other approach is known as cross validation.
No sharing. Thank you.
Okay. So the next approach is cross validation, basically. So what is cross validation? It is inside model selection package. You can see here. Okay, cross validation. What is cross validation doing here? See, in one shot you are doing it here. Here you are passing 5, right? You're passing 5. It means it will, whatever data it has, it will divide that into 5 parts. It will use 4 parts for training, 1 part for testing. Like you can see in the diagram below, you are dividing the data into 5 parts. This part you are using for testing, this rest of the stuff you are for training. Again, this part for, so different combination of it. Okay, so that you get more generalized model. When you go with this model outside, you should be able to tell, and boss, my model works with this much percentage. Right. So if you do so, you have different values of accuracies, right? And since you are given it 5, here you are given the model. Right? In one shot you are doing. Here you are giving x and y 5. So it is giving you 5 possible accuracies. What should be the one you will be claiming now, and what will be the claim? You will say, huh?
Highest accuracy.
No, not highest. You will be mean of it.
Yes.
Mean of it.
9.3.
Around 9.5. 95% accuracy you will see.
From that, we have to choose the model, right?
No. Model is fixed.
Okay.
Here, actually, remember the accuracy of model very much depends on whatever you are calculating. Very much depends on the training data. But you should, right? If you try to train and test with the same data, you'll always get very good accuracy. But that is not what is real.
Yes.
Right? So you have to make sure you properly test it out, see what is happening and all. Then you should be able to predict.
But the algorithm remains same, right? For the particular model, like if I have chosen, okay, for this data, I will use supervised. And it is only supervised algorithm which I use to train the data model, right?
Right.
So this is just saying the accuracy percentage. That's it. It won't change the model, right?
It won't change the model.
So output is also same.
See, accuracy is very important to identify how good is your algorithm. Should you try some other way? Or when you share your model, share your training model with the customer. So your customer also should feel that this is the accuracy. Okay, they should also understand that you're telling it. Like when you see matches and they tell 70% chances that India will win today.
So when you say I have to change the algorithm, is it like you're switching from supervised to unsupervised?
No. In supervised, in linear regression itself, there are a lot of varieties. Okay, that's what. So when you get a problem, first you have to identify it is a supervised or unsupervised. After identifying supervised, there is a flow chart.
It means combination of algorithms for particular problem.
Huh?
Multiple algorithms.
I'll show. See this diagram here. Oops, it doesn't know. Don't show it here. See this diagram here. So first, when you get it, first what you do? You do data gathering, right? Then you do data cleaning, data analyzing, visualization, getting data ready for machine. Okay, that is what we learn next. How to convert your data to numbers, right? All those things we'll learn. Text to integer, we'll do sentiment analysis and all that. Okay. Then you will identify whether this is supervised or unsupervised problem. If it is supervised, then you'll go for is it classification or regression. Right? If it is a classification, you will try out all possible classification algorithms. I mean, based on your understanding. Then if regression, you will go for all regression problems. Then finally your winner algorithm is here. So if you're regression, then you will try linear regression, random forest regression, all the possible of regression.
For classification, how many algorithms?
A lot of them. That's approximately like 50. No, not 50, 30 and all that. So see, there is broad level, you have this algorithm. Internally, there are some variations of it.
So we don't choose variations when we train a model. We just choose.
Yeah, I'll come to that. Model selection is what you're talking about, right? I'm about to come to that. How do you find the best model? What is the process? Okay, and before we go there, let's take 15 minutes break. Okay, this class will be till 1 o'clock. Okay, so take 15 minutes break. I'm pausing the recording. Let me remind me to resume it. Okay, so let's see. Okay, so basically, we understood, what we understood how to do cross validation. But the next point of our concern is how to choose the best model. All right, how to find like the best model and all. Do so. Okay, to do so, we have to learn one more concept. Okay, that is polynomial features. Okay, so as of now, we predicted a straight line. Many cases, our line with degree 2 can be a better case. So what we have predicted is a straight line. Okay, how do you okay, so this is x square, this is x cube, something like that it will be, right? Okay, this is a straight line. So how you really conclude whether your straight line is good or x cube line is good, x square line is good, right? So you have to find the best possible lines. Now we just predicted one line now. Okay, now we will understand how to find among multiple lines. Okay, and here I will explain a little bit of matrix operations. If you learn this, then we'll just touch upon make pipeline. 2 hours. Yeah, we would have covered quite a bit. Okay, you have understood the heart of machine learning. Okay, let's see now. Yeah, let's see now. Okay, so if you have to do all these things with multiple variables, okay, so just a little bit about what is a matrix. Matrix is n cross n. What is a vector? You have a row vector and a column vector. Row vector means all the data is along the row. Column vector means all the data is along the column. Okay, so suppose you have this data, whatever you're seeing here, right? Understand this thing. Okay, this is your house size. Okay, and let's assume for a moment you found out the best value of theta 0 and theta 1. Okay, so what does your line become? Your line becomes something like this, isn't it? Minus 40 is theta 0 and 0.25 is theta 1. Right, so this is your equation of line. Let's assume you found out. Okay, now suppose you have to represent this in a matrix format. This is reverse, huh? So how do you represent this equation in a matrix format? You have this, and also you have you want to predict the price of the house. Okay, so if you represent this like this, 1 1 1 and the price of a house size. First column is x is equal to 0 and next column is x, right? And you do matrix multiplication with these guys, minus 40.25. What is matrix multiplication? What is m cross n? This is one matrix, and then matrix is n cross c. The resultant will be m cross c, isn't it? Okay, so now here you can see here you have the house size here like this. Okay, house size here like this, and you have the theta. This is your theta vector. Okay, this is theta 0, this is theta 1. Okay, now let's see what happens when you multiply this. 1 into minus 40 plus 2104 into 0.25. This is what is this line, right? Okay, and what will be the result? The result is price of this particular house. This is how it becomes, right? So this is prediction is equal to data matrix. This is known as data matrix plus into parameters. This is known as parameter matrix. First question for you is, suppose you already know this and this. This is your output, right? Yes. You already know input and output. Can you predict this? Yes. Right. You have to find best value of this theta for which you are getting this. That's all. That is how you solve, linear algebra with matrix. Understood? Okay. That is first thing. Note this point. Second point is,
you mean we have price of the house also with us?
Yeah, you have the price of the house also with you. If you have to find what you have to do, you have to basically find this value of thetas, right? If you have that, you can easily do machine learning things here, right? Okay, to find the price of this theta. So now if you know this, all you have to do is find this for which you are getting this. That's all. You can do this with matrix operation very easily. Second point. Suppose along with house sizes, you have number of bedrooms also. Right. Yeah. Suppose along with house sizes, you have just for simplicity, I will not have this for simplicity. Okay, you have house prices and you want a quadratic equation. That means you are getting now h theta is equal to theta 1 x plus theta. You want to have something like theta 0 plus theta 1 x plus theta 2 x square. Okay, I want to find a chord. We have only one feature, but I want to find a quadratic equation, quadratic line. Understood, right? Okay, so for that case, what is the changes that I'll do here? Understood. This is what we have to do. We have to predict a quadratic line like this. Only one feature. Earlier it was predicting a straight line. Now it will predict a curvy line. Okay, so what will be my number of coefficients? First question.
3 coefficients, right?
3, exactly, 3 coefficient. So this is theta 0, this is theta 1, there will be another variable theta 2. Fine. Next question. Okay, what will be number of columns here? 3 columns. One will be x raised to the power 0. Right, this is x raised to the power 1. Another column will be x raised to the power 2 x square. We have all the x raised to the power 21404 square. 210 square.
This is what you're talking about, derived. This is what you're talking about, the derived one.
Yes. Okay, x square. Okay, so if we do the equation now, it will be 1 into minus 40, 2104 into 0.25, 2104 square into theta 2. Isn't this the equation? So now what happens? Now you can keep increasing the dimension of the data matrix. This is your data matrix, right? You can keep increasing the dimension of your data matrix. Okay, all you have to do, make sure you're increasing this guy. Output remains same as the number of data. Understood? Okay, now this is with one variable. Now if you make it two variables, like you have the number of bedrooms also in picture now. Okay, two variables, and what is the degree you want to consider? 2 degree. It will be what? X raised to the power 0, 1, then the coefficient part of it. Then it will be x, then x square, then y square, then xy. Understood? So that many number of parameters will be required. To see this more clearly, I'll do some examples. Polynomial degree. Okay, so what is this? Polynomial features. Okay, from this library I'm using this now. Polynomial features. What is the degree you want? 2 degree, right? 2 degree. Okay. Poly. Okay, now if you do poly dot fit, rather fit transform. Okay, this is your 1 data, 2 and 3. This is your another data, 4 and 5. If you do this, see what just got created here. First row, this is the x data, right? This is one row, this is second row. One row, second row. The first row get translated to this. What is this? 1, first thing, x raised to the power 1, y raised to the power 1, x square, xy, y square. Since we are given his power of 2 here. This is the matrix, data matrix that got generated out of data based on the degree that you are interested in, based on number of features. See the next line. 4 and 5, right? 4xy, 4 square, xy, 5 square. Order does not matter because all it matters is coefficient. Understood?
This first one is x for 0, that's x0.
X0, same thing, coefficients. Okay, x is per 0. So whatever the constant number it has to calculate, right? It will just calculate that and it will multiply it with 1 so that it retains that. So this is the data matrix. If you compare with this is this matrix. So now we know this matrix. We might know this matrix. It is very easy to find this data. Okay. Fine.
So what is the criteria to determine what order of polynomial should be selected? It's based on the features.
That is what you'll do. Given a data set, that is the question that everybody was asking. Right, given a data, which model is better? X straight line is better, polynomial degree 2 is better, degree 3 is better, degree 100 is better, degree million is better. Which one is better? Got it, right? So that is what we will find out now. Among all those possible degrees, which one is better? Clear, right? Understood. We have data points. Earlier we found a straight line. Okay, we'll do this in this case. We'll have a data point. We'll find straight line. We'll find degree with line 2, we'll find degree with line 3, we'll find degree with line 40, we'll see which one is better. Understood? Okay, which one is better? Let's see. Yeah. Now let's have some data and let's create a such situation, and we learn pipeline also in this process. Okay. let's now have I'll make two column feature. I'll take house price itself. Okay, just a real data. Okay, so what was the house? Yeah, so let me first load it. Import and speed. Yes, house price it. Okay, but we have to change a few things.
.csv dot
That is a file format actually. So you can see here this is right coming extra. So index column. Okay, what is the first thing you should do? House data dot info to check everything is fine or not. Everything seems to be fine, right?
Yes.
635. Okay, so now we want to calculate the price. Okay, based on square footage. Only one feature I'm using, or you want to use number of floors. Okay, I'm using for simplicity only one feature and then maybe two features. Total number of bedrooms, maybe these two features I want to use. So what is the first thing that I'll do? I'll create a straight line, polynomial line, all these multiple options you have to create. But there is a better way to do so. That is known as making this thing, making a pipeline. So what is the concept of pipeline? Okay, we'll see a simple thing now. Later we'll see much more. So concept of pipeline means you will have certain transformers, certain estimators. This is known as transformers. This is known as estimators. Okay, and what is transformer? Transformer, you will pass here data. Transformer will change the data to another format, and it will pass to estimator. Transformer will something is which is doing data changes. Like this guy, whatever I saw here, this guy is a transformer. Okay, it takes the data, it takes this data and changes it in this format. Okay, so these transformers, we'll see a lot of transformers will be required. When you get string data, your machine learning algorithms do not understand strings. You have to convert them into numbers, right? Your transformers responsibility will be to convert them into numbers. Got it, right? Okay, it's the responsibility of a transformer to convert them into numbers. Similarly, you are getting the data in this 2 to 2, 3, right? You have to convert it into something so that it can generate a polynomial degree algorithm, right? That is what this guy will do. Okay, so this is a transformer. Understand these few things. Transformer has three functions. One is fit, one is transform. Okay, and other is fit transform. What is fit? Fit means creating a mapping logic. Transformer. Okay, transformer transforms data from one format to another. There are three functions: fit, transform.
Always it converts to numbers, right?
Right. Fit, transform. These three logics are there. Okay. So what will fit do? Fit will basically create the mapping logic. Transform.
Mapping logic as in? Mapping logic.
See, for example, if I do a fit of it, just do a fit. Here, what you're telling here, that means you have to convert that into degree of polynomial 2. What does degree of 2 means? Degree of 2 means, whatever field. If you want degree of 2 xy, what is the degree of xy? 2. X is to power 2, y raised to power degree 2. X square, what is the degree of x square? 2. Got it, right? In polynomial regression, polynomial degree, right? You'll see what is the degree of this polynomial. You'll see the highest number is the degree of the stuff. Got it, right? So, mapping. What is mapping doing here? When you just simply do a fit, right? It internally creates a logic, so it is ready. If you pass data, it will generate into this format. It will not do it. If I simply call a fit here, it will create the logic, but it is not returning anything.
Blind.
Right now, if you do poly dot transform, when you pass the same stuff here, got it, right? So now it is transforming. Fit and transform is like both of these things happening together.
In that case, we can directly use fit and underscore transform.
Right. Okay. So, and now this is happening because we are giving a degree of 2. What will happen if I give a degree of 3? See? 1 x square x cube, y square y cube, x square y xy square. Xy square xy square.
X square x cube.
1 y square y cube.
So see this is xy x square xy y square x cube y cube xy square x square y. Fine.
Fitting just checking what type of polynomial it is. That's it.
Fitting is creating a logic.
Creating logic for that.
Suppose you have a string. You pass strings and each string has to convert into number. There will be some logic that will be created, right, which will convert string into number. That part fit will do.
Here in this case, it is creating a logic for the polynomial field.
What is the basis of that and how will it transform? It cannot give any random number.
For?
Like what is the logic behind that transforming into a particular?
You're talking about strings or
whatever it is. What is the basis of transformation?
See, in this case, the basis of transformation is a degree. In string case, you have different ways of doing the transformation. Count, vector, as it. Then you have TF, IDF. So there are different techniques here. So transforming, okay.
Depending on what you
right. So see, there are two things. One is transformers, other is estimators. Estimators linear. When you do model is equal to linear regression, that is an estimator there, which is capable of doing the prediction for it. Capable of doing the prediction for it.
So here you gave random numbers 2, 3, 4, 5.
The two data. 2, 3 is one data, 4, 5 is another data. Now you have transformers and one estimator. Fine, right?
I'm still not clear about this fit and transform. If I have a string data that is converted to numbers, that is done by fit.
No, fit will create the mapping. You can see fit is not returning anything. Fit is like, see, if I give you 10 strings and then you have to create a logic which is good for 10 strings, right? Right. Similarly, he gives you 20 strings. Your 10 string logic will be good, but it won't be great because you are mapping two words into one number. Right. So mapping will create that logic.
But there should be an algorithm behind it which runs, right? So who will Based on what?
So these are, when you say polynomial regression, it means there is one algorithm which is capable of whatever data it gets, right? It is capable of generating this. Okay, so whenever we see strings, as of now, just understand this part, polynomial regression. When you go to strings, we'll see lot many other things which will make it very clear. Okay, as of now, just understand it. What you are doing here, you are returning this object which is capable of converting any data. You can give more columns also here into degree 3 polynomial. Okay, so when you do so, when you are fitting it, in this case it just is it is getting it ready so that it knows, okay, there are 2 columns, 2 data which is coming here. So now if I do like this, error, right? Because we are not, it's not fitted for this. Whereas if I do directly, this is fine. By fitting, you are telling it that you get ready for this. This is what fit, that means creating the mapping, and after that you get the data and you do the stuff, right? Okay, you will get more clarity on the transformer part when you do more on strings. As of now, just understand that polynomial features is something which will be taking data, it will be converting to degree 3 polynomial. That's this part.
Our object is like for a given problem, which polynomial is better.
For a given regression problem, which degree of polynomial is better?
Accuracy.
Okay, so transformers, what is transformers roles and responsibility? Transformer role is to convert data into transform into some it has to generate this data matrix here, right? And using this data matrix estimator, like linear algebra, what will linear algebra do of this estimator? It will actually, what will linear algebra do? This is your data, right? Data matrix. Linear algebra will try to find out these values because it also knows this. Okay, let's now proceed further. So we want to use square footage and bedroom for price. These are the 2 columns we need to use. Okay, now see this code. Generative. Okay, so what you have to do, you have to create a pipeline here. Okay, so for that I'll use some okay, so what you're doing in this case, this is a linear regression function we have seen earlier. This is a pipeline here. Pipeline means something which will consist of transformer and this. Okay, we'll see now. This is very transformer and estimate. Okay, we have transformer. Transformer will transform the data, then we have estimator. Okay, so let's now dev. Return dot make pipeline. Okay, make pipeline takes transformers. This is a pipeline here. Okay, it takes your transformers. What is the input data to pipeline? It may be just 2 columns, so square footage and a number of bedrooms. Okay, and what will be the output of it? If you get giving degree 2, output will be x, y, x square, y square, and y values. Degree 3, whatever we saw, right? So based on the transformer, it will have different options. And estimator, what is our estimator in this case? Linear regression,
Linear regression.
right? Let's see. Okay, make pipeline. Okay, this is your DEGRE. So this will come from here, DEGRE, degree, right? This is the first option. Linear regression. What is the argument for linear regression? Intercept true, right? Fit intercept. Okay, it just created a pipeline for you. What you want to test? You want to test for different degrees, right? So for DEGRE in what is the degree? You want to test for 1 degree, you want to test for 2 degree, you want to test for, rather range 1 to 10 degree you want to test. Okay, this degree you want to test. Now, what will you do? Model is equal to polynomial.
One thing.
Uh-huh.
Just curious to ask you one question here. What is the need of fit intercept argument here?
This is, the purpose of fit intercept is to, in linear regression, we had this, right? This guy, intercept. So just to add this part, if you make fit intercept is equal to true, it will try to make use of this.
Okay. Thank you.
Okay. So, polynomial regression, you need to pass a degree. You are doing a degree here, model, right? Then what do you have to do with this degree? You have to do the training and all that here, right? Okay, I'll just write that part. Model dot fit. I haven't yet created my x and y, right? I'll create my x and y. This will be training the model. Now, after training the model, what you have to find out? You have to find accuracy. Accuracy of what we saw earlier was accuracy for classification, isn't it? Where you use scalar matrices. Now we have to see accuracy for linear algebra, linear regression, right? For that we have various ways. One is R2 square. Score R2 score scalar. If you do this, you'll get into this R2 score. This is the actual documentation where you see it will suppose this is your prediction. This is your true result. This is your prediction, right? If you do R2 score true by prediction, it will tell you what is the percentage. It will be between 0 and 1. Understood, right? It will be between 0 and 1 if things are fine. So this is exactly same. This is what it is getting. This is exactly this case, and you can get, if you see reverse correlation, right? You can get it as bad as -3 also, negative also. Okay, that means this, if it is close to 1, it means perfect. This is what you. -3, no, not median mean. It is like R2 score telling it how good is your regression algorithm. Understood, right? How good is your regression algorithm? We'll use this guy. Don't worry, it will be clear. Okay.
One thing, is it kind of L2 difference between two matrices or two vectors?
See, this is the actual data, and this is the prediction. You can see this guy is supposed to be increasing, and this guy is decreasing here, isn't it? So it is totally chaotic. I mean, if you get negative result, you think you have done something terribly wrong. It happened multiple times. Okay, let's see. Understood, right? Okay, so negative is definitely not expected, that you have done something terribly wrong, and these are the numbers which are good to see, right? We are expecting 3, you get 2.5, and expecting -0.5, you're getting 0, 2, 7, right? So pretty much in line. Let's see now. Okay, so now one thing we didn't do, so now we have now loaded the data, but we want to extract these two columns from it, isn't it? So x is equal to one was this square big, right?
0, comma
SQFT. What is the next one? Okay. Of course, you can use all of them. This is x. Price. This is y. Okay. Then you have this x and y. So of course, if you train the model, now you have to. Of course, what is the thing that we didn't do? We didn't divide into train and test, right?
yes.
Okay. Okay. So I'll just mention it here. Okay. So insert below. Okay. D1. My data into train and test. Okay, so we can steal the. Of course, we can use cross validation. Of course, I'll make it train size should be 0.8, say 0.7. 5. Okay, so you have x and y. It splitted it, right? Then what you want to do? You want to test with x1, y1. Now you want to find the results, right? Y pred is equal to model dot predict x2, right? Then you have to find accuracy of the model, right? You can use R2 score. Then you come here, then you have prediction and you know the actual result also, right? So you do print degree for it is white true first, right? White true first. Y true first means y2, comma y pred. This is your degree of it, right? So if everything is right, it should do the stuff, isn't it? It will try for 1 to 10 degrees, show the accuracy. Bang. Yeah, so after that it is all insane. So till this point it is fine, right? And in this point also something around accuracy 3 is giving you better, isn't it? Okay, but mind it, you are just using here very small number of features, right? So if you give, understood, right, what is happening here? If you increase the number of features,
So here in this case we have very few parameters. Let's say if we have 100 parameters and that gives like 95% accuracy. And with just 2-3 parameters, it gives like 85% accuracy. So in that case, like which one do you prefer?
So you definitely choose what are the important features. I mean, we learned that with random forest and correlation techniques that really helps you understand. I mean, this is a very simple case here. Where I'm
in this case,
so in this case, in this case, right? I mean, very much depends. I mean, you really want to make the model very simple, right, with less number of features. So your variability is less. You're more generalized.
So less variability, less parameters. Even if the accuracy is less, we still go with that.
Right. Little less. It's not that you are saying. Yeah. So in this case, we'll see few things again. This is with all the features. This is X data. This is Y data. This is your splitting part. Train size, right? Splitting part. This is a model that you are creating. This is the degree. The accuracy has gone quite bad, right? Okay, just let me do one thing. This is the data I've tested with Y1. Right, you can see this one is the highest and this guy is the lowest. But what we are doing here, we are actually testing it on the training data itself.
Yes.
Right, and we're using all the features and all the things. We didn't do a lot of other things here which we could have got positive results. So now let's understood, right? A model is created. Which one do you think is better model? Fourth one, right? 89. Is there anything higher than this? It's okay. It's the model, right? So we want to say use this model, right? We want to save it. You're just seeing a simple process, okay? That how now you found that degree 4 is giving you decent results. Okay, let's see now. What you want to do here is you want to use this particular model. So when you are creating this model, I would like to save this model also. Models. This is one common approach. So either you save the best model or you can just do a append here and push the model. Fine. And what is the degree? So degree polynomial is and you are pushing the model over here. Okay. So that fine, right? If I run it,
models.
Oh yeah.
After that.
Oh, sorry. Okay, so this way is fine, right? Model 4. So how to get access to this model 4? Models 4. If you want to use it for prediction, and what will you pass here? Huh? Yeah, but you need to convert that into this is the model with degree 4, right? Yeah, so you have to convert the data into also degree 4.
Yes.
Right. So to make use of this, so first you will do polynomial features degree 4, right? Pol 4, right? Then you will use pol 4 dot fit and transform. You will use one of the data. Let's say you will use this data.
The first 4 features or anything else?
Okay, this is the 4, and also this model itself has this thing, right? I don't have to do this. Yeah, so I just need to pass models 4, right? Models 4 will give me access to that, isn't it? 1, 2, 3. It will be 3, isn't it? Because I'm accessing from 0, 1, 2, 3, right? Model 3 and do a predict. Right, we got this 46,000. This is the price prediction. What is the actual price? It is somewhere around 65,000, 62,000, right? Of course, there is a it's not the best algorithm because we haven't done a lot of things, but this is the process. Got it, right?
But this time was part of the training set also, right?
Which one?
The first data that you just passed it.
Yeah, this is passed to the training set itself.
So when the part of
So yeah, we can actually it is randomly choosing. We actually don't know. Okay, we have to see it. If you do x1, no, that was not part of the data set.
Which one did you pass it? Okay, something else.
X and Y, we pass two different things, right?
It was split data.
Yeah, so we're passing really the unknown data here, if you see.
So if the number of features is 3, how will you make a whole number of orders of 5 or 6? Number of features is 3 or 4.
Let me just pass this data 1 second. No? It is 356 number. Huh? Okay, so don't judge it by the one element security. It tries to find a generalized formula. So the overall accuracy is good. So see the way. So this is the data. You're just passing it to predict. It will automatically. It is auto. I don't even need this, right? I'm not using this. Right. So it is automatically doing the transformation and then predicting it because the pipeline has it everything. Right. Just that we have stored the pipeline here. Okay, so you got the 72,000. Let me just quickly check. It is what? 356, right? No.
One thing, I have a question. So considering the pipeline mechanism, right? What is the estimated part here? Could you please highlight that point again?
Yeah. So the estimated part is the linear. See, this is the pipeline, and in the estimated we have this. This is the last guy in it, right? This is the estimate.
Okay.
Okay, so we have different data here, which is getting transformed and all. Okay. 356. X2 log 356. Yeah. So this was the stuff, right? And you can see anyway, X not, oh sorry, you have to do in entire X. Oh, that was the way it was done. So where is the price? No. What was the name of that entire data? House data, right?
House underscore data.
Yeah. X is the selected one. I haven't selected it here. House data is the one. Yeah, that is where it should go.
You can put Y of
that also I can put definitely. I just wanted to print the entire page. Oops. Okay, so you can see the price is something like this, and we are predicting 73,000, right? Okay. Any questions? You saw a beautiful small pipeline here. Okay, you're trying with all different degrees here to see which one is, giving you better results.
But it's asking like if there are 3 features, okay, how will you predict? How will you create a multi-order, like for example 6-order polynomial?
It is already doing it.
But how, like that is on the machine, but how will you do it? There is some coefficient which is coming as 0, right? 0 the expression.
You want to see the coefficients, right? Oh, okay, just a second. So here there will be something. Actually, the coefficients and all we'll see using on the estimator. So what is your question?
For example, if there is a bedroom, and if there is square feet, and if there is like, okay, these two are there, how will you create a 6-order polynomial without of it?
Oh no,
only
it cannot.
x0 and x1 is there. How will you create?
X cube. X raised to power 4.
So, but that is again like a derived one. So
that is what it means.
But how does it help?
So what you're trying to say is you have x and x and y. Y is your y is your value, final outcome dependent variable, y is x. So it is sometimes possible the data is like this, right? Right. If the relationship between the data is like this, x raised to the power 4 may be a better way to tell the relationship between them. Got it, right? It's typically sometimes it can be x raised to the power 13 also.
And this x raised to 4 will be the best value will be given by. This x raised to 4 will be the best. Okay, got it.
Got it, right? We'll try to. That's what we'll do in this process. Okay, this is only the score part. Of course, you might want to know the cost, right? For linear regression, so go here. Okay, I'm just telling you how to do it. So there are a lot of ways. You go here, you see classification matrices are there. Okay, go down, you'll find regression matrices. What is the thing at which we're using mean square error, right? Go here. You see mean squared error. Okay, and this is what we might be interested in. So let's see. So in this case, mean squared error. Okay, do this like this. Mean squared error. The third parameter, right? Mean squared error is equal to these are your different error mechanisms. Okay, so it too is y1. So you can see here. Okay, you are getting mean squared error. You are getting the equality here.
This is like exactly equal to cost function.
We have degree for so
right.
This is 7 hours.
But
no, this is for eternal constant.
Okay, got a hang of these things, right? Save in chest point.
If you want the coefficients, we need to go to that particular model dot
field and do that. I mean, the way we did for first case, right? .of
On what we have to do it? Is it on the model?
and the estimator. Estimator is a linear regression, right? Here it is entire pipeline that you have. Okay, so right, understood the concept of pipeline, right? Pipeline consists of transformers, estimators. We need to get to the estimator to get all these things. Let me see if we can get it directly. I'm not. You see here, if you want to know about the pipeline, you can do it like this. M steps, if you do polynomial features, is the first degree 4, right, for this particular degree thing, and it is telling you the linear regression is acting after that. Then you have, I think they get answers to show. Or, right, you can see the stuffs here, right? This is what it is doing. This is the polynomial degree bias, then all the stuffs.
Oh, is this model model parameters or
right? This is the entire pipeline information because M is your pipeline. Okay, I'm just trying to see. Okay, got a hang of it, all these things. Just proceed a little further. Okay, we'll see more things like this. So the journey is clear, right? How you do it. And just for regression, I haven't yet spoken about, strings and all that. So now let's see some strings.
I want to till now we did not deal with the loss, right? We just created a model and performed prediction. That's it. Okay, whatever the loss we observed from the true value, we did not process it, right? We just
this is so loss is basically what was predicted and what you got.
Yes, that's right.
Right. So this is what you're seeing. This is the loss here.
Yeah, MSC. Okay.
Okay. I mean, the loss on these all parts are parts of accuracy. So whenever you have to find accuracy, right, what you should go is you should go into this level. Okay. This is the full sheet. Okay. These are the lot of options are there. Okay. Don't worry. The first thing is don't worry. I mean, if it is lot, that's why the learning curve is this way. Okay. So other things are just variations of it. So what we are talking about mostly is, loss in regression or loss in classification. So these are a lot of varieties. We'll basically use accuracy, okay, confusion matrix at times, precision score at times. The regression of these things are there.
Okay. But so whatever it is, whatever the methods, whatever the procedure we use, the loss is the approximately same across, right?
It will be very difficult to say yes to that. Okay. I'll give you one example why I cannot say yes to that. Okay. Suppose you lose your mail classification accuracy is 99.99%. Very good. Okay. Right. Okay. But what is the case where it went wrong is typically one important mail it sent to junk folder. That is more severe compared to a junk mail coming to your important folder, isn't it?
Yeah.
Okay. So that's why I cannot say that, if loss of one variation or other, definitely a loss means something. I mean, that is where it goes next stage. Okay. Each loss, that precision comes with each loss means something. But at this point of time, it's okay. Okay. But know the differences that these things vary into.
Yes.
Okay. Now let's see for string data. Okay. How do you? That must be question in your mind as of now, right? Okay, numbers we understand, we can do whatever we want. Let's now see for string data what happens. Okay, so for string data again, there are what do you say? A lot of that is known as featureization basically. Whenever you have to convert string data into numerical data, that process is known as featureization. Okay. Okay, that is also known as feature engineering. Okay. Okay, so I'll use another note because okay, so there are a few techniques of feature engineering. Okay, so first is given a text, I'll use some real data set. Okay, so what will I do is I'll try to load some data which has some strings in it. California births HR data. I load this HR comma separator data. Okay, this is like I think I did it for this last time also, right? HR data. Yesterday on right. Okay, let me load some. That's okay. Since we know it, I don't have to. Okay, I'll just do string handling here. But read CSV. Okay. Okay, you can see here a lot of numerical data, but two columns are strings, right? The salary column and this is the department. This needs to be renamed. So what will I do? I'll just rename it. How did I rename column rename? I keep forgetting this. Renamed column rename. What is it? This. Yesterday only we did it, right?
Rename it as one.
Rename? No.
Rename sales.
Oh, just rename. Okay. Sure, I've noted it right.
And then in place equal to true.
Let's see. Where is it? Yeah. Rename. Yeah. No. Acha. Sales, why didn't you change?
Then we did HR data dot head.
Yeah, that is for just getting first 5 records.
Yesterday only we did. That was rename column or column rename. What was it? Edit. That's it.
Google it. Just Google it.
A day ago, I think this is what I was doing yesterday. Right? I always, because the word is little flipped out.
Data dot HR.
I forgot actually. That's okay. Okay, I'm not changing it. I'm keeping the name as sales only. Just check out yesterday's.
Columns equal to, then in the bracket you have to put it.
Columns equal.
Columns equal to, then
Columns equal.
This is no, this is not this one.
No, not like that.
no, in the column.
I was doing that, right?
No, just no, before out of the,
Oh, that you have to pass all the things.
no, columns equal to, then first,
First bracket and then column.
no, columns, no, you don't need to put it equal to, now that bracket,
Control is that.
Open bracket.
open bracket,
It's a data.
columns equal to, and then in the first bracket,
Here only, right?
hmm,
I did that.
no, columns equal to, then first bracket.
Yeah.
Again, one more.
Oh yes, the same mistake I did yesterday, right? Yeah. This is always yeah. Sales. How do we remember this? Sales and department. Yeah, and then you do in places. Yeah, you.
Here, columns are put in here.
HR data.
Yeah, you noted wrong.
No, here has to rename.
The first
Data
column.
dot-
First column.
Data.
First column.
No, top
HR underscore data dot rename.
rename.
Oh,
First
rename.
column.
Yeah,
first
rename.
Oh,
Yeah,
you noted it right, huh?
Rename and then. Yes.
Yeah, I think you-
also did same thing. HR data.
Right. I always. Yeah, this is right. Okay. Oh, anyway, come back. Okay, this is. I don't know why they have done it like this. Okay, so here we have HR data. So what we want to do, you have lot of possibilities of options, right? What are the possible department? Do this. Department unique. Oops, sorry. You will get that all these possible varieties are there, right? So you don't string anyway, your data cannot be processed. So what you want to do, you want to convert this into numbers. So for this is 10, 8 or 10 fixed varieties. So your label encoder is the way from sklearn label encoder.
Label distance.
sklearn pre-processing import label encoder. Okay, so LE is equal to label encoder. Fine, right? Now you have to pass it this particular column so that it transform it back into numbers, and we want to override the previous string data. EEPT. We want to overwrite here. I don't want to see the numbers. So LE dot fit transform, doing both of them in a single shot, and you have to give here the column name. Now do HR data. You'll see all numbers. See this department. Yeah. 1 to 7. You've changed the contents of it to numbers. Understood? The same way you will do the other guy also, salary. Right? But remember, each thing will be passing different this thing. Right?
Same number.
Same number with that.
No, because all of them were same. Yeah, first few were same actually.
Your table.
Yeah, I'm doing last layer. You'll see the part. Whatever is showing. Okay, see the entire thing. Understood, right? 239. Okay. Then you have
HR
this
data dot dict dot unique.
Yeah, you'll see all this. Right, all the possibilities are there. Now what is the next thing? You have salary also, right? Salary also you can do the same thing.
Same label encoder. Use
label encoder for this type sort of things. I'll show you different ways. If you have review comment, you have lot many words, right? Then it will be a different ball game. We'll see that first. Let's see this.
We have to first import it, then we can pass in
HR data salary. So now if you do HR data, see salary, low, medium, high change into this.
How it changes this values?
So internally what it does when you first you're doing fit and transform anyway, but actually it's fit first. When you do fit first, whatever data you are given, right, it finds how many buckets do you need. Okay, how many buckets do you need? One bucket for IT, one bucket for sales, one bucket for HR, right? Different buckets are there. Okay, you are creating the mapping. Okay, given 10 data, 5 data is given for me to create buckets. I create 5 buckets, and now whatever string you pass among these 5 buckets, it will bucketize into them. If it is not in this, it will use some other technique to find some generalized one. It will decide the number of buckets based on the fit function. Understood, right? Clear? That means this first level encoder. This was the easiest one. Okay, there is another way, and remember, if you have this sort of thing, right, you might want to have different columns for different department, so that you can get better results. Sometimes this will give you better result. Sometimes if you have different department, like one department column is there, right? This is one technique that you can see. Now one department column we want to convert into multiple columns. If it is sales department, this guy will be 1, all other will be 0. If it is HR department, this guy will be 1, all other will be 0.
Yeah.
That sort of thing you want, then that is known as, there is another technique that is known as dict vectorizer. Okay, so I'll again load the data. Okay, so we have again seen what we want is different column for us, right? Okay, so you have something known as from sklearn dot pre-processing import dict vectorizer. So how do you know from this library? Just go here. This is like Bible, all the documentation, everything will be fine there. Okay, so go to pre-processing point here. Okay. Oh, feature extraction dict vectorizer. Okay, now what you want to do, you have this department column, right? So do this first. dv is equal to dict vectorizer dv dot fit transform. Okay, what do you want to do? HR data dot department. Oops. str fit transform HR data. What is the error it is saying? So what is it? Fit transform department. Let's see. HR data. Sales. Yeah, that's right.
Isn't transferred.
See, you have this. I've created a vector here, right? Two arrays just to show it actually. So the vectorizer. Acha. Oh, it may be the case. Okay. HR data. Yeah, now it is fine, right? Okay. Oh, sorry, what I did. It is doing this, and then dv dot fit transform HR data. What is it? As though actually items such it needs the data to be in dictionary format. Actually, give a second. Yeah. So what it is saying in this case, right? It is looking for items. That means it needs the entire data in dictionary format. Right. Okay. So I'll just show a simple case. It needs you have a disk. Okay, just pass column and like a name, say location if you have. There's another way of doing it. Location, say Mumbai. This is one data. Location.
You cannot mention like this, right? Maybe you should know if there are more.
No. We'll do it that way. So this is one. Okay, I'm just need to see. Right. So if you now do a two array, okay, you see here it created two columns for you. Right. I'll just I'll just check. Okay, maybe you have to do fit separately. So this is, so you want to know dv dot feature names. If you do this, it will give first column is for Delhi, second column is for Mumbai. Right? First column is for Delhi. So whichever Delhi, suppose you have more data here, right? Which is again the same Delhi. You do this, see? The second next to guy has Delhi is equal to 1, right? So this is, you're generating columns here. Okay. To do so, internally you have something like one hot vector, right? One hot encoder. Okay, we'll do such things now. All right, this is the stuff. Okay, we are getting into strings. Okay.
Is there an advantage if you do like 0 ones instead of
Yeah. There are some advantages. Okay. The thing is, if you have multiple columns, you might get better results in many cases, right? Because it means you are giving weightage to different columns.
But again, other things are 0, right?
Right, other things are 0. So what it means when you are seeing something, from Mumbai location, if that thing is very important, many times by making it multiple columns, you might get better results. Right? Because what happens when you have a column is you are telling it this is a new feature. Delhi is a feature compared to you have one value of a feature. So these two things are different. So that these things also you will try it out when you are creating your algorithm, right? These two things you will try it out and see what is happening.
Also, the weightage will be same for the weightage will also be same.
Weightage will also right. Right. Okay. So then you count vectorizer. How many times? I will resume this actually. Okay. So we have count vectorizer. What is count vectorizer? How many times a particular word is appearing in a text? Then you have TF-IDF. Okay. So we'll continue with featureization. Okay. I'll be uploading this code. Okay, Sunil, I'll be Sunil and Somdev and folks who are only available online. Who else? Yeah, Venkatesh. I can see your name here. Okay, so I'll be stopping the recording and I'll be uploading the steps and recording transfer. It will take some time to translate the entire step. After that, I'll be putting it. Okay. Take care, everybody. Tomorrow we'll catch up at 9 o'clock again.
Yeah.
Okay.
Today will be uploaded, right?
Yeah. See.